My name is Frank Nelson. I'll be your instructor for this module. This module introduces the new memory controller support in the 7 series family of FPGAs. After completing this module, you'll be able to describe the new I/O features for supporting high-speed memory controllers in the 7 series products. Now, this content has been broken into 2 different recordings. We're first going to give you an overview of the memory controller support that we offer, and then we'll talk about the phaser and the I/O FIFO functionality incorporated. Memory technologies are continuing to evolve, as seen from this graph. It is clear from market data that the DDR3 is the highest volume DRAM technology and will be for the coming years. Now, DDR2 is the legacy technology, and there may be some interest for new FPGA designs in the low end for compatibility with legacy products. However, this interest will quickly fade away. Now, mobile DRAM and LPDDR with the latest LPDDR2 is supported at 1.2 volts will become more popular, especially with handsets. And as demand increases, the new memory controllers will be more attractive in more FPGA applications. These are a couple of the memory technologies that are important. QDR2+ is the latest evolution of the quad data rate SRAM. QDR is different from DDR. It is a static SRAM, is very fast, and has a relatively big memory cell. SRAMs are lower in density than DRAMs. DDR3 has a smaller dynamic memory cell. Its density gives it a big advantage, but its reads are destructive, and the memory cells have to be refreshed, and you have to do page management when copying data as well as other commands. So there is a lot of overhead in using a DDR3 memory in terms of functionality that must be built into the memory controller. DDR3 provides a huge capacity at a reasonable bandwidth, but with a sometimes unpredictable latency. QDR provides medium capacity at twice the bandwidth at a very low and predictable latency. And this is very useful in telecom applications. In addition to the QDR2+ SRAMs, the specialty DRAMs like the RL DRAM are widely used in networking applications as a trade-off between the commodity DRAM, such as the DDR3, and SRAMs, such as the QDR2+. They offer DRAM-like density with performance closer to an SRAM in random accesses. The key to understand is the memory controllers are constantly improving and gaining more advanced functionality, and Xilinx is, of course, working hard to keep up the pace. Memory bandwidth is almost always the single most important performance bottleneck. It is important to realize that your overall system performance can often be very dependent on the available memory bandwidth. Thus, there is a continual push for higher and higher bandwidths from all 3 of the newest memory technologies, that is DDR3, QDR2+, and RL DRAM. The rate of increase of memory bandwidth per pin has far outpaced the overall increase in performance of the FPGA fabric. Conventional methods of using FPGA fabric to implement a high-speed memory controller as soft IP is simply not sufficient to meet the speeds of the newest memories. To compensate, designers will try to widen the data path to 32 or 64 bits to improve the data throughput. But the caveat, of course, is pin layout, power consumption, and cost of materials associated with high pin count packaging and the use of slower I/O standards. So just widening the data path is not a solution for the newest technology. Now, as this graph highlights, FPGA fabric speeds have trouble keeping up with memory bandwidth speeds. To meet system performance, designers need a mixture of soft IP that allows designers flexibility and hard, fixed technology that supports the highest memory controller performance. So what is needed is a different way of building memory controller physical interfaces. Soft memory controllers cannot perform at speeds needed, so these need some improvement or to be fixed as a hard macro so they can meet performance needs. But designers prefer to build their own memory controller to get the features they want. The I/O interfaces in the 7 series are high performance. This is especially true if you increase the auxiliary voltage domain, which is used to power the I/O pins, and thus increases the I/O performance. The problem is that the DQ and DQS signals of the interface will require some special logic. This is especially important because designers like to customize their memory controller, and thus it needs to be built within the FPGA fabric. So this means a mixture of programmability as well as hard logic in the IOBs and the clock management tiles that are going to have to be made. We will also need to have some rate multiplication and make sure that we use the SerDes functionality of the IOBs as well. Well, now that we've gotten a feel for what the industry demands and the applications that are possible, now we can start looking at how Xilinx has chosen to address some of these issues with the technology embedded in the 7 series. So we're going to have a look at the phaser and the I/O FIFO resources. So the phaser feature of the CMT and the I/O FIFOs are designed to resolve all these issues. Now please note that these features are available in all 7 series FPGAs regardless of subfamily and device density. Now DDR3 memories operate in byte lanes. Each byte lane is 8 or 9 bits. 9 bits is sometimes used to use the parity bit. Some customers will build a 64-bit data bus and use the extra 8 bits for error correcting codes as well. Now there is one DQS pair for each byte lane. On writes, the DQS must be center aligned, while on the reads, it is edge aligned. So these phase relationships will have to be managed so the data can be sampled properly. Now, while pushing data off the FPGA can be accomplished, the challenge is with reading data from the memory onto the FPGA. The DQS is not a clock. It is only driven when data is being received from the off-chip memory. So you can't really just use a PLL. You'll need to use something more sophisticated than a PLL. Well, with these problems, this is where the I/O phaser really helps in giving you a good solution. You should note that to reach the peak performance required, the phaser logic has to be fixed relative to the I/O pins and the clock management tiles. Now, on the left of this diagram is the conventional I/O interface using the IOB resources. We can see that the DQ is a tri-state implementation, as we would expect. The DQS is a bidirectional differential signal. Now, we have the SerDes logic dedicated in each of the IOBs for just this kind of situation. The middle layer in blue is all in the clock management tile resources. And this diagram shows the new stuff that has been added to the 7 series, namely the phaser in and phaser out resources. As you can see, there is a PLL with each clock management tile. The PLL is used to generate a reference for the phaser in and phaser out blocks. In previous generations, this would have been sufficient, but with DQ and DQS signals requirements, we need to be able to not only generate out multiple signals that are accurately out of phase, but read in similar signals as well. Now, the phaser in monitors the incoming DQS during memory reads to generate the iSerDes clocks. The iSerDes clocks are placed in the middle of the DQ data I. This is done dynamically and is stable across process, temperature, and voltage. Similarly, the phaser out uses the PLL reference to generate the OSerDes clock for the DQ. It also generates the DQS, which must be 1/2 bit period out of phase. Now, this is done with extremely low jitter and duty cycle distortion. You should also note the iSerDes transfers the capture data in a 1-to-4 mode to the hard input FIFO block, and the OSerDes transmits the data in a 4-to-1 mode to the hard output FIFO block. Now, each byte lane will contain 12 pins. It could be 8 or 9 data pins, depending if you're using the parity bit. It'll also be 2 DQS clock enable pins and 1 data mask pin. Now, each I/O bank can support 4 byte lanes with their size, and this is enabled simply because of the migration to a larger size I/O bank. Now, within each byte lane, pins are predefined, so you'll need to check out the pin-out tables for the correct connections that are appropriate. To support 4 lanes in one bank, you must use an internally generated reference voltage. So, since this is because not enough pins are available for an external VREF. So the data has now been clocked into the SerDes resources in the IOBs, and now the data in each byte lane has to be combined together into a FIFO. This will bring the data from each 466 MHz clock, note that's out of phase, into one memory. So the data captured is generated by the iSerDes, OSerDes, and it's running at half the rate of the SDRAM. So the read and write data are on separate clocks. Now the data must be brought into the I/O fabric, and that is because it needs to be at a lower clock rate internally. All byte lanes need to be on a common clock and managed by the input and output FIFO blocks. The I/O FIFO clocking uses a DQS PHY aligned clock on the I/O side and uses fabric clock on the fabric side, which eases the fabric design and decouples that clock from the I/O side. So this will provide a 1-to-2 and 2-to-1 serialization deserialization with a 233 MHz fabric clock for about 1,866 megabits per second I/O rate. Now let's have a short summary before we invite you to check out part 2 about our memory controller features incorporated in the 7 series family. Now all 7 series FPGAs have dedicated hard logic for implementing the physical layers of the high-speed DDR3 and quad data rate 2 plus memory controllers. And this includes the dedicated phaser in, phaser out, FIFO in and FIFO out logic resources. And these blocks work in conjunction with the other logic in the I/O and the clock management tile columns to generate a complete physical layer for these memories. This includes the iSerDes, OSerDes, and the PLL resources that are already part of the FPGA. So to this point, we've had an overview of our technical solutions that are included in the 7 series products to aid in the development of memory controllers. We've talked about some of the dedicated resources, specifically the phaser and the I/O FIFOs that are dedicated in the 7 series devices. Now we're going to get into memory controller construction and what are some of the best ways to build your memory controller. So as you know, memory controllers store data in banks, pages, and words. And of course, depending upon the type of operation that you're using, then this is going to have different sort of requirements. And that's because the DDR3 SDRAM is going to organize that data, and it requires different operations to access the data. So activating to open a page in a bank, doing a pre-charge to close a page in a bank, of course doing read-write transactions to access and modify data, and of course to refresh the dynamic RAM cells. But the key thing here is to understand that the timing between the commands is complex and crucial. And this is one of the reasons that it's so important that the memory controller be built properly. And this is because no one-page management policy is going to be ideal for all applications. So what is best is to use the IP for the memory controller as part of the memory interface generator. So that's our best solution. So we've already got pre-optimized components that are going to take full advantage and allow you to build the memory controller you'd like. Now it's very challenging to try to do this on your own, but it performs the operation reorder for efficiency, and it's based on the Virtex 6 DDR3 memory controller. So our technology is proven. The controller itself operates at 233 megahertz even though the data rate is high. Now the MIG, or the memory interface generator, is included with the core generator as part of the ISE and the PlanetHead software, so it's included for free. The DDR3 core is also free. Now the DDR3 memory controller is provided through the MIG, and it's leveraged, but it's built upon the Virtex 6 FPGA DDR3 reordering controller architecture, which supports a programmable bank machines for high efficiency. So the key thing here is to understand that it's going to utilize the new I/O and the clock management tile features of the 7 series, and it's already pre-optimized and pre-verified. So it's been tested extensively and is used by many Xilinx customers already. It also includes a number of advanced features, such as a 1/4 rate for higher data rate speeds, up to 1,866 megabits per second, with a 28 nanometer fabric speed. It also includes a self-refresh for lower memory power consumption. Now there are 2 user interfaces that are provided with the memory interface generator. There's a native user interface, which is leveraged from the Virtex 6 FPGA MIG memory controllers, and it can be used in legacy designs as well. There's also the AXI 4 interface, which we've been moving to, which utilizes the AXI 4 protocol, and we recommend for new designs, and is required if you're building multi-port designs. Now both solutions provide a high single speed and a wide interface to the memory controller. But note now, the AXI is not a PLB bus. It's not tri-stated, it's not multi-drive, and it's not a master-slave. It is designed as a one-master, one-slave protocol. So if you want to learn more about this, for more information, you can check out the AXI interface from the support.xilinx.com website. So as we mentioned, the AXI 4 is by nature a point-to-point protocol, and this is best supported with complex systems, and they're often built using the AXI interconnect blocks. Now an AXI 4 interconnect block can be used to create a multi-port memory controller, and this provides a configurable number of AXI 4 protocol user ports. And each port is independent but accesses the underlying memory controller. So it does support different clocks and port widths in its application. Now the AXI 4 interconnect blocks are provided by Xilinx, again, as part of the IP from the EDK toolkit as well. So now let's spend a few minutes and have a look at the memory interface generator, the MIG. Well, it's always easiest to build your memory controller by using the memory interface generator, and that's because it allows you to customize the memory and the interface to the memory controller. So it allows you to customize that architecture, the data rate, the bus width, the CAS latency, burst length, and I/O bank assignments, which is all critical to the performance and the application of your memory device to the FPGA. It also generates the RTL source code and your constraints from a hardware-verified IP file. Now, the memory interface generator is delivered as part of the ISE software and also operates under the same kind of core generator interface. So once you find the core generator, you'll easily find the memory interface generator. Now, the memory interface generator supports for 7 series devices. It includes the DDR3 SDRAM, the QDR2 Plus SRAM, and the RLDRAM2. Now, the LP DDR and the newer controllers will be added to the utility when they're available. And since this recording, they're probably already included. And we encourage you to check out the sample design that includes the DDR3 controller. If you want to build your own controller, there is also documentation about the physical interface. But as you will see, the MIG will require you to know the device, choose the type of controller, choose the interface, any DDR3 options you would like to select, the input clock options, and also then to go about defining where you would like your pin locations. Now, pin allocation is simple with utility, and it assigns byte lanes to an I/O bank. So it makes it really simple and very optimal. Then integrate your UCF file, which you might need to customize the prefixes of your pin assignments as timing constraints. And then the PLLs will be required for the DDR3 use in each I/O bank. Likewise, the MMCMs can do everything for the PLLs that you need to actually for your clocking resources. After launching the MIG from the core generator interface, you use the wizard to set the system and your memory parameters. The wizard will generate your RTL and the UCF files, which are the HDL source files and your constraints files. Now, these are generated from a library of hardware-verified designs, and your inputs are used to directly modify these files. The code is not encrypted, and you have the flexibility to change and customize the RTL files at your choosing. After the optional code change, you can perform additional simulations on your design. The next step is to import the files into the ISE software project, followed by synthesis, place and route, timing simulation if needed, and finally verification on your hardware demo board. The next few slides are just screenshots of the memory interface generator wizard. Here is where the MIG verifies your design settings, which are imported from the ISE software or the plan ahead software. If you wanted to change these settings, you'd have to go back to those project environments, those utilities, to actually modify those settings there. Here is where you choose what memory device and configuration you're choosing to work with. Many of the most common chips and DIMMs can be chosen from the drop-down list. Parts from different manufacturers are often compatible, so even if you are using a different part, one of the selections of the drop-down list may be appropriate for your application. If necessary, you can create a custom part by entering all the timing parameters of your new device and then in the Create Custom Part page. Now, the tool will then determine how many parts, and hence DQS pairs, are used from the data width selection that you customize with the GUI. Now, the wizard also allows you to customize the AXI interface if it was selected as your chosen protocol. The data width, address width, and ID width can then be customized here from within the GUI by the user. Now, the wizard enables you to set a variety of options like the burst type and termination options you choose. Some of these options, such as the burst type, will be sent to the DDR3 SDRAM's mode register on startup. Now, this page also allows you to determine how the flat address presented to the user will be mapped to banks, rows, and columns. This page allows you to configure what kind of system clock will be used and whether to use the internal VREF, or reference voltage. If the internal VREF is not used, then the VREF pins on the FPGA must be used, and this will prevent having 4 byte lanes in a bank. Bank selection for your I/O pin assignments is one of the more important assignments because it determines the board layout and is recommended before any board layout plans are done. Because the pin mapping within each byte lane is fixed, aside from the DQ pin swapping within the byte lane, pin selection is relatively simple for the user. That's because the MIG does any error checking between what the FPGA requires and what is optimal for the memory controller you're building. Now let's wrap up this recording with a short summary. Now, in summary, all 7 series FPGAs have dedicated hard logic resources for implementing the physical layers of your high-speed DDR3 and QDR2+ memory controllers. This includes the phaser in, the phaser out, the FIFO in, and the FIFO out dedicated hardware resources that are part of each I/O pin. Now, these logic resources will work with other logic in the I/O as well as the clock management tiles columns to generate a complete physical layer for these memory controllers. This includes resources like the iSerDes, the OSerDes, and the IOBs, as well as your PLL, which is in the clock management tiles. Now, all these hardware resources are used by the soft memory controller generated when you build it with the memory interface generator. So it does all of this work for you. The MIG will generate a complete memory controller with either a native user interface, or it can also be customized by you to use the AXI user interface. Well, there are lots of 7 series information at support.xilinx.com. For the sake of this topic, I recommend you refer to the 7 series FPGA Memory Interface Solutions user guide. If you would like to learn more about our course offerings, you can go to the training webpage you see here, and there you can learn more about our course offerings, including the Designing with 7 Series Design Family course. You can also look at what other RALs are available to you for free. But in the end, what we ask you to do is take a minute and let us know what you think of this recorded learning. Give us any feedback on the next page. All you need to do is click on the next page and you can find the icon to submit your evaluation. You've been listening to the 7 Series Memory Controllers RAL Part 2. Again, thanks for your time and attention. Thanks for listening, and thanks for your business.